So this problem dealing with normal and tangential acceleration has a box that is at point A, and it moves down this conveyor belt, and at first it moves in this straight line, and then when it reaches this point right here, it moves along this curved path, and we're asked to determine the magnitude of acceleration at point B, which is right here. And how do we go about this problem? Well, the box starts at rest, so it has an initial velocity of 0 meters per second, and it increases at an acceleration, a tangential acceleration of 0.2 t meters per second square. Well, what does that tell us? This tells us that our acceleration is not constant, so we are not able to use the kinematic equations. We have to figure out a different way to deal with this acceleration. Well, how do we do that? The tangential acceleration is equal to the dv over dt, and this is equal to 0.2 t. So what we can do is we can separate our variables and we can integrate. So if we have let's just look at this part of the equation, because we are substituted in what at is. So let's move this dt over to the other side of the equation. I'll try to keep some color coding going on. So we have dv is equal to 0.2 t dt. So we've separated our variables, and now we need to integrate. And when we integrate one side, and we integrate both sides, and we're going to integrate from a final velocity, so some velocity that we don't know, to an initial velocity. And our initial velocity is v naught, and we know that v naught is equal to 0. So instead of an initial velocity, we can just put from v naught to 0. And we want to integrate from a final time, some time t, to an initial time, which is 0. So this becomes the expression that we need to integrate. Well, when we integrate this, we get v is equal to 0.2 t squared divided by 2. And we can simplify that a little more, so that 0.2 goes away and it becomes a 0.1 t squared. And this is going to be evaluated at t, and this is going to be evaluated at v. So it won't, if we evaluate that, we get v is equal to 0.1 t squared, just like we did before, just like we had before. So now we have an expression for velocity, and we also know that a velocity is equal to the derivative of x with respect to time. And just like we had an expression for acceleration, we know what our velocity is. So if we substitute our v in, we get 0.1 t squared is equal to this dx dt. And again, we want to separate and we want to integrate. So we want to 0.1 t squared times dt is equal to, let's use green, dx. And now, how are we integrating this? Well, we're going to integrate from a time t to a time 0. And we have to figure out the bounds of x at which we integrate from. We know we're going to, at time 0, it's starting from rest up here, so we're going to call this position 0. So we're going to go to 0, but how far are we actually moving? Well, we can figure that out. We know that a is going to move from here. It's going to move from here to here in a straight line, and then a circular path from this point to this point, and we have a radius. So how far is this? Well, we know it's going to be at least 3 meters plus whatever this distance is. And this distance is circumference of a circle, which is 2 pi r, divided by 4, because we're only using a quarter of the circle. And if we put in our numbers, we get 3 plus 2 pi times r, which is 2, over 4. So this goes away, this becomes a 2, that goes away, and we really just get 6.14 meters. So that means we're integrating from 6.14 to 0. So when we perform this integration right here, we're going to get, this becomes a 0.1 times t to the third over 3, evaluated at t to 0. So t to 0 is equal to x evaluated at 6.14 to 0. So this just becomes 0.1 t to the third over 3 is equal to x. So now we have an expression for x. It's not equal to x, it's equal to 6.14. So now we have an expression that we can solve for t. And if we solve for t, we're going to get 3 roots of t, and we're going to get that t is equal to 5.68. The other two solutions for t turn out to be complex solutions, and we just aren't interested in them. So it takes 5.68 seconds to go from point A to point B. And we want to determine the magnitude of the acceleration at point B. Well, we're going to need to know 2 things. We're going to need to know our tangential acceleration, which we actually have an expression for. It's equal to 0.2 times time, and our time is 5.68 seconds. So our tangential acceleration is 1.138 meters per second, and we need a normal acceleration. And the normal acceleration is the velocity squared divided by the radius of curvature. We know the radius of curvature, it's given, it's 2 meters. So we just need to figure out what our velocity at B is. And we do have a expression for velocity, which is right here. It's an expression for velocity because of time. So our velocity is equal to 0.1 times our time, 5.68 squared. And so our velocity is going to be equal to 3.23 meters per second. Now we can put this into our velocity up here, 3.23 squared, and our normal acceleration is going to be equal to 5.21 meters per second squared. And just looking back, this should be meters per second squared right here, because it's an acceleration, not a velocity. And finally, we're asked to determine the magnitude. So the magnitude, our total acceleration, is equal to the square root of our tangential acceleration squared plus our normal acceleration squared. So it's equal to 1.138 squared plus 5.21 squared. And this is equal to a total acceleration of 5.33 meters per second squared.